He is a senior scientist and UARC fellow at NASA Ames Research Center for Nanotechnology, PhD in physics from University of Florida, Gainesville, and the winner of multiple awards from 1997 for his work on CNTs, which I guess 1997 puts him right at the start.
Okay, so after Brad's talk, I'm afraid I've come to this conference for the first time, and it has a little bit more technical information, but I'll try to take you through the main points which are relevant to the space elevator perspective. And part of the reason I came is I've been working in nanotube area for quite some time now, both on the mechanics, thermal properties, electrical properties. There are a lot of applications, but here we'll focus on the mechanical aspect. So some of those, part of the reason I like it because I do computer simulations and modeling using various approaches from quantum mechanics to molecular dynamics and multi-scale like mesoscale and so on. So you get to make these colorful, nice images. And second point is, you won't see it again, that in nanotechnology, one new thing is there that the size of the material and the systems that is continuing to shrink, and then your computer simulation capabilities and accuracy of the methods and computer power available to you is increasing. So there is a good overlap between what you can get out of simulations. So the claim is that, and that we have shown quite a few times now, that we can do predictive work and so on. And then I'll show you that in this space elevator, this is a rather recent of my exposure to it, so I'll try to relate it to it and see where we can contribute in this area. And this particular segment is based on nanotubes. So this particular chart shows you different forms of carbon. Two bulk forms are well known, graphite and diamond, that are shown, but in mid-80s, fullerene came along, and Smalley and Curl and Kuto, they got Nobel Prize on that. And early 90s, carbon nanotube came along, which is shown as the cylindrical molecule. So way to conceptualize is that basically you take a flat single sheet of carbon atoms and fold it into tubes so that bonding is perfect, no defects, and ends you can cap by this half fullerene or half soccer ball kind of structure. Part of the reason it is very mechanically strong and also high modulus and so on, because it's a material, it's perfect, there are no defects and so on. Part of the reason bulk material like steel or alloys or something, because they have bulk defects, that's where the problem comes in. Now since you are making the material at the molecular or nanoscale, that's the reason, because they are not, that's one reason. Second is carbon-carbon bond, which is a variety like covalent kind of bond, so it's a strongest bond from the chemistry perspective. So there are very good reason for it to be lightweight and very strong and stiff, and it has shown both in experiments and so on. This is one of our earlier slides, and I just picked it up, setting up this. We have like programs in materials, sensors, electronics, nano-related things in there. And this is the nanomaterials roadmap in there. And you see, so this is like, so here we are talking about nanotextiles or woven fabric or nanotube composites and so on. So roughly like this kind of time frame, 2000. So CNT carbon, so this is a concept like artistic thing for elevator was there. It is there in our picture too. So it's not only for space elevator, but suppose this kind of material can be made so requirement for a space elevator is you have 100 gigapascal at 1.3 gram per cc density. So of course this is needed for space elevator, but even less than that there are other applications for from NASA perspective. So that's the reason, and that so that cartoon image it was there like in even 97, 98 when this thing was made. So that's the concept of So we call it CNT tether. So with this much background, this is the outline of my talk, and I'll go over the main points of it, and I'll not get into the technicalities of it. So if anyone has interest, they can pursue with me later on through email. They can take my talk. So I'll talk about the basic concept about like this tensile strength. That's a big issue, where this is coming from and why those numbers. Then especially from application perspective is at nanoscale numbers are very good, but we cannot have application at nanoscale. We need like a lot of at the macro scales or very like you can say meters and mile long objects. So question, how do we scale up from there? So in that process, what has been the recent progress? So I'll not again review the whole progress, but I've selected few papers which will give you the basic feature and then what are the drawbacks and what can be improved. And so I'll try to take you to that part, and that will bring you up to the current state. So in that sense, I'll talk about ultra long nanotubes, carbon nanotubes, the spinning of nanotube bundles into yarn or a fabric, like that's what was mentioned in the last talk. Then models of mechanics, means how do you derive those properties or how do you get that, which is actually coming from traditional, more like a textile mechanics. Then scaling, how do we, so when we make the fibers at the nano scale, but we want at the micro, macro scale, so there is a degradation of the properties. So how do we scale up from that, and what are we losing, and what are the assumptions in there? So those are the points. If we continue to build it in a systematic way, then at least we know what are the limits, and then we have to think about how do we overcome them. So that's how I'm trying to build up my talk, and towards the end is I'll show you some examples of what we are going to do within the next 1 year, which could contribute towards this field. So this is, and some of it is like my work, and some of work I have chosen the selected paper from the literature. This was my earlier work in the nanotube mechanics, where you have this single wall nanotube, like you can compress it and so on. These kinds of simulation. This is just to give you an example that you can run them, and change in the color is basically the change in the stress and strain in the system. Similarly, you can stretch them and so on. This was kind of twisting. Oh, it didn't show it there. Okay, so that's just example. You do that. But compression, since compression, and then we did some verification from the experiments. I will not go into the detail, but apparently for the space elevator application, tensile strength is more important. So let's talk about that in a couple of minutes. So tensile strength is the strength at which the material will yield or break. So when it breaks, breaking is always related with the formation of some kind of defect in the material, and that defect is called in the technical language and the community is called the Stone-Wallace defect. What is a Stone-Wallace defect? Is that nanotube is made up of, in the beginning I showed you graphene sheet, and graphene sheet a hexagonal chicken wire lattice structure, and those, so basically it's made up of hexagons. So in the hexagon I can turn around in that lattice and rotate just one bond. If I just rotate one bond, so that hexagonal sheet and that local structure will become a defect, which is shown here. That you will have a heptagon here and a heptagon here and two pentagons. So this is called 5775 defect, and that's called Stone-Wallace defect. So that is the beginning at which you have the nucleation of this defect. One will form, two will form, the material is continue to stretch further. That's how it will break. So essentially, what is happening, and that's the beginning of the breaking of the material. So if we can figure out what is the activation barrier and how long will it take, what is the tensile strength, and that relates to the tensile strength actually of the nanotube itself. So in the beginning, earlier days when simulations were done, that they predicted very high, like 30% yielding strain, which is 30% means that if I take a nanotube and stretch by 30%, then these defects will form. So that is related. And the reason percentage, and one way to connect or keep in your mind, how do I relate it to the tensile strength is, so Young's modulus, or modulus of these materials typically 1 terapascal. So if I take like 30% of 1 terapascal, that will leave me 300 gigapascal. So 300 gigapascal is a very high value, even no experiments measure that, right? So when experiments occur which is at 6% or 12%, so that will correspond to 60 gigapascal or 120 gigapascals. That was it. So there's a big difference between the two. But then simulation. So we investigated this issue a little bit more closely and really did a lot of these dynamic simulations where formation of the defect as a function of temperature, as a function of strain rate, and so on. And came up with the number, and so this is yield strain is 9%, 9 plus minus 1%. So if you take typically, if your modulus is about 1 terapascal, if you take 9%, let's say 10%, so that gives you some kind of magic number, 100 gigapascal. So in that, and nanotubes density, single wall nanotubes density is 1.3 or something like that. So it does satisfy in that sense. So that was, and that kind of, I guess I was not aware of it, but since as those numbers started to come in, so that got probably Brad and other people in the space elevator community enthusiastic about a material like nanotube. So this is single wall nanotube. When you go to multi-wall nanotube, we extended that model. I will not go into detail how and why we did that. But look at that other chart. These are all papers published, so if you're interested, I can send you some information on those things. So it turns out that, and this is also the tricky point, actually the tensile strength at which the tube will break, this also depends on the rate at which you will stretch the material, strain rate. If I, in a sense, think in that term, like if you apply the strain very fast, that means you're shocking the material. So then it will break at a different strain. But if suppose, this is almost like an engineering structure for like long time duration, 1 year, 2 years, 3 years, 4. So for example, what here I'm showing you, that this is just a model, like you've shown a double wall tube, which is a model of a multi-wall tube. So black line is for a multi-wall tube, and the red curve is an equivalent single wall tube. So you see, generally black line is better than, so defect-free perfect multi-wall tube saying that its tensile strength would be even better than single wall nanotube. And then upper like, so these kind of strain rate are simulated in the simulation, but these are more realistic. At 300K, this corresponds to like 1% per hour. In simulation we cannot, but there are physics-based model we have created, which I described in this paper with it. But then even that is not important. So if you go the other arrow, so now I don't have the pointer, okay, here. So if I go to this arrow, that corresponds to like 1% few years. So a few years, so then you can go to like, even if you come to here, so let's say in terms of duration wise, like you can come to number like 10 to minus 11, that comes to few tens of years and so on. So you want that kind of a range. So, and those kinds of ranges, your black line is above the red line, that means that defect-free multi-wall nanotube would be better than single wall tube. Now again, let's make a jump. But this is still, those nanotubes were made at the nanoscale. So nanoscale obviously is coming from the diameter, but length is very important too. Length means that you are making like few tens of nanometer, few hundred nanometer, few micron. That's pretty much it. So in terms of the progress wise, this was one recent experiment done by, there quite a few groups have done it, and this was, I think, was the Los Alamos group and Duke or Carolina, they were involved in that. And so they show you, like if you see the top one, they show you almost like a 40 centimeter nanotube, single wall nanotube they have grown. So one thing when I looked at it and I thought, wow, if it's such a big scale, then how can I see the nanotube? There must be some problem in there. But it's not the problem. So what they did is that that data which you see, that really 40 centimeter long nanotube, you are not seeing the real data. They created the image from that and superimposed and just add it up. So in naked eye you should not be able to see. If it were single wall nanotube and if it were like, you will not, because technically you are. So always be aware of this thing, that you are dealing with something you will not be able to touch easily, you will not be able to feel, you will not be able to see, but you should be able to control it so that you get some material which is at macro scale, that is our observable material. So that's why I put this slide there. But then on the other side, these are very strong proofs. Those peaks you are seeing is the Raman spectra peaks and so on, and that's the tube. So that's a very strong signature, and they have taken that peak at different different lengths in those tubes. So that's a very strong signature that this is indeed a single wall carbon nanotube. So that's a good progress, that under certain conditions you cannot make it a lot of them, but at least you can grow them long. So there was one thing. Second thing, then how do I move from like these nano scale to the macro scale, and that's also recent progress. Again, there are quite a few groups are doing that. Cambridge and Dallas and then they call it, I cannot even recollect. Right now about 6 or 7 have shown pretty good progress, at least in my mind. So I just picked up one paper which was coming from UT Dallas, where, so now you take this nanoscale fiber, and then the idea is, can we take this nanoscale fiber and then weave them like yarn and come up to the macro scale, which would be used in other projects, a space elevator, a sky hook, or some other tether application. So this shows you, this video shows you one weaving example, that you are growing on a substrate, nanotube like a jungle, and then you just reach in there with a pointer. It's almost like a old days of making thread. You go in there and since you are spinning at a certain state. So this particular spinning was done by hand, and at the most their hand is stretched back up to 1 meter. So that's the length. So that's how that grew, and this is 2004. It's not too old. So that's where we are, right? But it's still, actually, this gives you an example that you can, and there are groups actually, electro spinning and laser based spinning and so on. They are started to do it, that as the material is growing, nanotubes are coming out in a CVD kind of process. Then you can grow them continuously. So there is a hope that it will. So this is the earlier work I picked up. So using that weave yarn. They have gone to the next level. They have single ply, like 1 ply, 2 ply, and also 4 ply, and polymer. You build up it, so that's your fiber we are talking about. But then if you do that, you start to lose the original properties. So these are some experimental measurements. So I think this A corresponds to the single ply, and B is double ply. And C is for this with the polymer, and that gives you also the idea about what kind of tensile strength we are talking about. And these numbers are fairly small, because if you look at B, that's about like 400 megapascal. It's a very small number as compared to, we are talking about gigapascal, right? So what is happening, and that's where the problem comes in, and that's what we have to figure out. One, and second, we have to figure out how to improve upon that. And this is again, I just picked up one paper. I'm not saying this is state of the art. So there are which are showing 2 gigapascals, 3 gigapascals, but still not too much. Like and this unpublished work you were quoting 10 gigapascal. I have not seen that, but up to 2 gigapascal I've seen in the literature. Now let's go from there. So that brings us to, again, I think that's where we'll contribute. What goes back to these theory and modeling guys. So this is one work. It's by, again, Byron Pipes. He used to be at NASA, probably, I think, and now at Purdue University. So this gives you some model of again, I think it's coming out too low, so let me try to explain it. So what you do is that you have the nanotube bundle, and so what you do is that you nanotube bundle and you spin it, in the theory also, you spin it so that it's introducing some angle of helicity or chirality through which you are rotating or twisting this material. So this particular graph, maybe I should not have shown so much detail. Directly, let's go there. So this particular graph shows you, this is the modulus, ratio of the modulus of the twisted fiber versus the original straight single wall thing, how much it is degrading in the property. So you see, like, and as a function of that helical angle, and the helical angle is that twist angle. So even when you are going by like 10 degrees, 20 degrees, 30, 40 degrees, so this thing has degraded by almost like 40-50%. Like one, you started from 1, and for means 60% you have degraded. So even if for the pure material you had like 100 gigapascal, so these are the scales. So by just doing, even at the nano scale you have not increased from nano to the meso to the micro scale, but even at the nano scale you have degraded the modulus by about 60%. So then you come to that material that 60% of 100 gigapascal will come down to not you degrade. So it comes down to about 40 gigabytes. It's not too bad, but it's still degrading. But that is degrading at the nanoscale. Then there's another model to do it, but I'll not go into the detail because I want to leave some time for question and answer, which gives you also the similar number. This is another model theoretically how to get an estimate, ballpark estimates of those numbers. But let's come to this. So here, then this gives the idea of how do we move really from nano to micro scale fiber, and this is about the scaling law. So scaling law is that I take this nanoscale fiber, twist them into a yarn, then they take this and take this yarn and then again have a collection of them and twist it into a bigger fiber, and then have a collection and twist into a bigger fiber. So there is something called use of self-similarity for scale. But at each scale, when we are mixing these things up, by volume fraction is going down by 20%. So, and then when you go through the arguments and so on, actually, so number wise, so here you see this is single wall nanotube, this is a nano yarn, which is they did in the experiment, and this is a micro scale fiber, and this is really the microfiber which they can you can have 50 to 100 micron diameter. So this you can handle it and so on. But then the problem is when you go from there, then you look at this graph. This is single wall nanotube and it has degraded by that much. So keeping this is a bad news, but it's not so bad because at this stage, because it's not so bad because this model, this is simplistic model coming from continuum theory. It has a lot of assumptions and approximation. We do not know because so you look so when we come to microfiber, yeah, here's microfiber. You see, so it's kind of carbon fiber. In carbon fiber, you're already making them, right? So what's the degree? So that shows. So, but we have to really check this point in the sense this is like you are making a nanoscale material and bringing out to the macro scale. But the question, which is from the science technology point, is if we bring out to macro scale, whether we lose the nanoscale property, we have to be able to answer that. So that's one of the critical issue, and that is not. It's generally it's of interest to us, but it's of interest to Space Elevator and also Sky, who call the communities as well. But then this is still not bad news because in this model, the way it's done is there are a lot of approximation assumption. So we have to start going into that and check one by one, and I think things can be improved. I'll show you some examples. For example, for the same model, so for the same model here you see this is for the Young's modulus, which is for the stretch, but this is the shear model for the same thing. So these 3 points are good, but you see carbon fiber point is so high, and that shows you some kind of inconsistency in that model. So let's see, how do we improve that? So that gives you another thing is that this is a good news part is that. So part of the reason that is losing the value is coming from two reasons. One is that when I scale up the material, when I take the bundle, when I take the nano to make a bundle, I'm introducing these empty spaces in that. It's a simple geometrical construct, and that empty space reduces the volume fraction. At the most, you can have 79 or 80% volume fraction because you always interstitial space you cannot avoid it, right? So that means that you are losing because of that. Second is that your load transfer between these material is not perfect. So for these two reasons, you use that. So this is one example that is just answer one question. So this is an interesting experiment. You take a bundle and then you irradiate it with electron beam. So what it does is that, and if you tune the electron beam, if you do that, that creates the intertube linking. So in a sense, I still have the bundle, but now tubes cannot slip against each other. So that gives you some kind of thing. And then if you look at this graph here, so you see this is the irradiated bundle. So this is the electron beam radiation strength. It's about, if you are here, then you see you are getting 3 orders of magnitude increase in the value of the bending modulus. In this experiment, they didn't do the stretching modulus, but they have computed the bending modulus. They put it on a straight, and then tube is bending like that. But we know that there is a relationship with connect bending modulus with the stretching modulus as well. They almost linearly. There is some proportionality constant. So this is a very good news because it says if you can get a 3 orders of magnitude increase in the bending modulus, then you are getting some very good increase in the stretching modulus as well. So we have to start expanding. I'll not go into this part. So then, so second part comes in is that, so that tells you, if I somehow can do interlink these tubes in those bundles, I can increase their stretching modular, tensile strength, all those things. Remember that tensile strength is related to the stretching modular by just the strain value at which it will break. If it's 5%, 10%, you just take that number. That's why I showed you in the beginning. So now, and this shows you the example. What is the role of this? What is the chemistry at the interface? That is not well understood. These are some unknown things people have to start working on. And some of this is what I show you two examples. This is our own work. Is that one example is nanotube polymer composite, because one idea is you are going to use polymer to strengthen the material. So in this case, when we did that, this is a polyethylene nanotube composite few years back. So you see that increase in the value in the Young's modulus is, it's about like 40 or 50%, not too much. 40, 50% of the value of the bare polymer, not the nano. Of course, you cannot increase the fiber, but you increase the composite over the matrix, and then matrix was the polymer. So whatever be the value, you can increase by 40, 50. Okay, so. But we know that in this polymer interface is very weak. So nanotube slips or fiber slips within the matrix material. So if we change that, go to material like silicon carbide or something. This is just an example. I'm studying silicon carbide in a different sense, silicon carbide nanotube composite for our own some high temperature application. But this is just to show you the, because here now it forms a different interface. That was weakly interacting interface, this is strongly interacting. In the sense nanotube really forms chemical bonds, so it's kind of anchored in the material. So if you do that, then you are getting much more. So if I look at these numbers, so then for the same volume fraction, here my increase is 250%. So I'm getting from 30% to 200. So these are just giving you the examples. What are the control factors you should look into to really design the material where you are going? And I'll not go into. And here, so like silicon carbide pure density is about, that's what I'm asking, about 2 gram per centimeter instead of 2.63. So I'm coming from, and then if you take like 56 gigapascal, right? 250 gigapascal if you take, so that goes to about 120 gigapascal. So there are different, these are examples is there. So you have increased the weight little bit. So then that could be a play factor. How much weight do we increase, and then how much tensile strength do we gain? So polymer, is it a good thing, or maybe we just do some site-specific chemistry and do some interlinking? So there you have to mix in all these things to design those things. Now this is the one of the towards the last slide. So we have started to do that. I was telling you in the previous model of the scaling that there is really based coming from the continuum mechanics and so on. There we are coming right at the right time. So now we are taking in the simulation a bundle and then like twisting it and simulating. So this is some preliminary results. This we have not published it yet, and I'll just put it in here. Just show you an example. That's where we are going to contribute to give you some realistic number in terms of what would be the numbers that would be of interest to this community. So here I show you an example of a rope or bundle which is twisted by 10 degrees, and I'm seeing from the top. So you see this flower is a structure like that, and here is a 20 degrees. But you see, this is 45 degrees. At 45 degrees, when I see from the top, you see it starts to break. So that gives you itself, because where is this strength is coming from is because when you twist it, you are twisting it like this. So what that does is that for the tensile, it is creating the compression force along this direction. And if you continue to do that, that really breaks off the nanotube. So 45 degrees, but that's not a bad number actually. It turns out, and then so what it happens is that twisting itself is going to increase my load transfer between, and those are the things that were not included in the previous model. And with that, let me try to end that. These are some of the things. So basically towards the end, I'll give you some example. What is the status of the field? How do you think about this problem? How do you estimate it? And what are the experimental progress? And the question is, what do we do from here? So two things I did not talk about. One is I'll show you one example of MD simulations that we have started to do around this twisting of the nanotube in the yarn. Other is if we want to take this MD model into the macro thing, then we have to be able to do mesoscale more correctly. And that's another thing we have done, and I did not talk about that. Thank you. Thank you. Oh, in those twisting things?
When you twist them together, you got a reduction versus angle. How does that work? Basically, length.
No, so length does not come in because twist itself you define by twist per unit length.
Okay.
Right. So
it goes through five twists or five.
yeah, something like that. Yes.
So if you made it like longer, the curve would essentially shift up or down. If you change the length, it shifts up or down.
Yeah, it sure, but one way to think about it, and that's what we will check actually in the next 4 or 5 months. That study, which is based on continuum, that says that you are getting the optimum compression and optimum tensile modulus when your angle is about 10 degrees. So just keep that in mind.
Well, you said it was supposed to be like all the new
No, in that particular thing, they have chosen about, I think, but it's still micron size, like I think 500 nanometers or something more than, but it is still very small. So that's why that model, which is really coming from the textile mechanics. So they did it at the nano scale, but it is still 500 micron scale, you can say. And then they did the scale up to the microfiber. So there are certain approximations in their original model and the certain approximation in the scaling up process. So we have to go and start checking those things step by step. Then we can come up with some reasonable better number. Second thing is that in those models in the continuum mechanics, they are not still talking about the tensile strength. They are just talking about the modulus. Simply because in the continuum mechanics they won't be able to do it. So if we can scale up some of the MD simulation, we would be able to address tensile strength directly. There are certain other approximations there, tensile stretch is uncoupled to the shear or the bending, but we know that they are not uncoupled, right? So those are some of the things. Sure, yeah.
I was just wondering, instead of like twisting or braiding to get the diameter of it, is there any reason why you can just apply like you had a double tube? I mean, it's narrow a way. You can just keep applying the tube over top of it, like 10, 20, 30 layers thick, or does it make it too stiff or?
Yeah, so we are talking about multi-watt tube. So multi-watt tube essentially has the same limitations. It is at the nanoscale object. So at some stage we have to do that. So that twisting experiment was done by multi-watt tube. But then what happens is that if you conceptually if you think about, if you keep on filling it out and you come to the micro level, so then basically it's essentially carbon fiber.
Right.
So it would be very stiff and so on. It will lose a lot of properties. Yeah.
You showed the rabbit peak. Would the sharpness of that peak be related to inversely related to the defect rate? Does a more perfect nanotube give a finer peak, at least in theory?
It could be, yes.
And when you spoke of the volume fraction going down 20% in the garden,
Right.
is that at each level or overall from nano to meso?
At each, yes. So consider the I'm making like I have a circle, right? Now I'm packing the circle into replace. So I'm leaving those spaces because I cannot really completely fill the space. So it's just coming from the geometrical concept. So at each level, at nano level, from a single tube, I have made an array. So then I lost.
So at each yarding, there is a 20% volume.
Yeah, you will. So you keep on reducing that. So, and that's part of the reason that in the end, when you come up to the macro level, you have lost so much by the volume fraction itself, and that's why you're losing the value. So somehow how do we take that? And that's actually I did not mention, and that's what I think the trick is. If you then, and that's why I made the initial comment. If you look at the technology, how they did it, they are spinning by hand, right? So it's very loose spinning. So I think the trick would be that you have to come up with some nanoscale spinning technology itself.
So that's good. My third question was going to be, you spoke of starting with bundles at the beginning of the yard. Those are self-assembled, grown as.
Yeah, those are self-assembled.
Roughly, what was their size? How many nanotubes of nominal diameter would be in the bundle that you started with?
Right. So typically nanotube is 1.3 nanometer diameter is, but then that bundle itself would be of around like 100 nanometer or like something like that. So
So pi r squared tells you it's a lot of individuals.
That's right.
Okay.
Yes.
In your charts, it was sometimes hard to see the
Yeah.
axis, but it looked like he was we said the strain rate in some of the early simulations.
Yeah,
was
yeah.
1 picosecond, which
Right.
is practically explosive, I thought. You said it's at 1% per year. Where was?
Oh, so then there's a model actually. So actually in MD simulations have the limitation because in your atomic frequencies are typically of the order of femtosecond. So even if you run like million steps and so on, you come to picoseconds and nanoseconds. So how do we make the jump? So we figure out what is the mechanism, and then the mechanism corresponds to some kind of an actuation barrier, and then there is a prefactor. Once you can figure out with that, so that's a physics model based on transition state theory. So if I use that, then I can put in any number there. So I can make a jump to per year, so that's what we have done. So you can look at the paper. Model is there in the paper. So we used MD simulations to fit the parameters of the model, and then we extended that first to a strain rate like 1% per hour, which is like an experimental strain rate. So then we see we fit the data, so that's the validity of the model. And then we say, okay, let's suppose if we increase it to per year, what is the risk? So you are building up again this system. Yes.
For space elevator application, this tether would go up through the NL belt and would be subject to considerable radiation load.
Right.
And your presentation indicated that exposure to an electron beam can actually create some cross-linking.
That's a good news.
That's good news.
But that's a bad news too.
Yes, right. That means the mechanical properties of this tether would be changing as a function of time.
Yes. So there are other issues. Right now, my feeling this field is so young and so new. All we are talking about is very base and bare material, because this is a big problem for NASA for other things. So, like for example, like all the spacecraft. So this is a big thing. Like we have radiation, we have other particles like micrometeorite and all those things. So how do we do that? Like so my feeling is that on top of that, even if you make a carbon nanotube based material or some ribbon, you will have some coatings, and that's a separate issue. So if you want, so in a sense they will not be exposed to that. Yeah. So even if you are okay with this base material, you have to be able to protect it, because oxygen will leak it up. There are so many kinds of atomic compartments or ionic compartments are coming in. So yeah.
The other question has to do with what is the rate of creep as a function of the stress?
Rate of creep, I've never heard of that. So I don't know.
In most materials, for example, in electrical connectors, you want a certain amount of clamping to make, but that clamping force diminishes with time due to creep.
Right.
And this is usually temperature dependent. It's also dependent on what kind of alloy you have.
Right. So let me turn that around actually. For the space elevator application, what would be your rate of creep? Ask someone else. What we have done is there's a model. If you tell me what would be the rate of creep, then I tell you what the tensile strength. So I will turn it other way around. So you have to get that answer from someone else, and I'll give you the answer.
By the way, on the radiation, they have done radiation studies with the radiation from Nano on carbon fiber, which has largely similar atomic binding structure.
To be fair though, the LDEF passive exposure, no, we don't see.
That's not that.
These were not strained.
These weren't LDF exposure. This was in the lab exposure with radiation.
With 20-ton strain?
Strain on carbon fiber, not on the carbon fiber.
Okay.
Very advantage of the nanotube.
Okay, so we have to move on to one last question and then. Yeah. Oh, couple.
Couple of comments. One is that creep of carbon fiber is one of the lowest of any materials that exist.
Oh, it's longest?
It's the lowest.
Lowest.
The second one is that you express surprise with respect to the lower shear modulus of the twisted yarns and bundles, even lower than that of carbon fiber.
Yeah.
It's actually not surprising because carbon fiber is made of graphite crystallites. They're randomly oriented around the axis of the fiber. And some of those crystallites basically interact on their edges, which has a stronger bond. So it's those edges that are providing the higher shear modulus in the case of the carbon fiber.
I completely agree with you.
If someone had asked me that why there's so much difference, I would have given the same answer. But we need to check that. That's the reason I mentioned here, is that because amount with which it was with respect to this, that part is kind of, we need to check that. Because that I agree that carbon fiber is almost like a solid. That's what it's saying, solid and bonding and so on. So shear would be going up, but this is an idealistic model. It does not have the details. So that's the reason. If we start to give in detail, will it go up and then the Young's modulus actually remain at the same level? That's in that sense, I said that. But I agree with you.